angle between the directions of the two vectors. So that's what we call a scalar product. Now, let us have some notes. Note. Today, among the facts on this scalar product, that when theta is acute, meaning that it is less than 90, then the cosine of theta will be greater than 0. The cosine of theta will be greater than 0. And so A dot B is also greater than 0. That is very, very true. It is going to be a note here. You need to note that. It is very, 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 very true. And if theta is obtuse, meaning that it is greater than 90, then the cosine of theta is going to be less than 0, and also A dot B is going to be less than 0. I want people to take that note. Now, what if you have two vectors which are perpendicular? If two vectors A and B are perpendicular, then it means the angle between them is 90. It is not less than, it is not acute, it is not obtuse. It is just a right angle. It is 90. But we know very well that the cosine of 90 is going to be 0. So the whole right-hand side is going to become 0. And so the scalar product is also going to become 0. So if vectors A and B, let us talk about the angle. That if the angle between vectors A and B is 90, or if vectors A and B are perpendicular, if vectors A and B are perpendicular, i.e. theta is equal to 90 degrees, then we know very well that the cosine of 90 degrees, or the cosine of theta is going to be 0. So our A dot B is going to be 0. That is very, 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 very true. Now, what if A and B are parallel, meaning that the angle between them is 0? Oh, very interesting. If vectors A and B are parallel, what do we mean here? I.e., if the theta between them is equal to 0, then we are going to discover that the cosine of theta is going to be what? Is going to be 1. So our A dot B is going to be the magnitude of these vectors. So that is for parallel vectors. So if it is any kind of proof or showing left-hand side is equal to right-hand side, or show that the vectors are perpendicular or parallel, then we need to quote these notes. Hope you are going to put these in our books using your handwriting. So immediately after a break, I'm coming back with more notes about our scalar product. Now, I want to add you another note. Hope you have copied the previous ones into your books. Now, the phrase, the angle between vectors, always refers to the angle between the directions of the vectors, when these directions are either both towards their point of intersection or both away from their point of intersection. We can put that one down. The phrase point of intersection. So the reason why I'm giving you such notes, I want people to note the facts about each subtopic. If it comes to scalar product, there are some facts which we are supposed to know. And one of the facts is this. People in their diagrams are going to get difficulties in getting the angle between the vectors. Something which is very simple. So I've quoted it for you. That the angle or the phrase, that is the angle between two vectors, always refers to the angle between the directions of the vectors when these directions are either both towards their point of intersection or both away from the point or from their point of intersection. So what I'm trying to mean is this. If you have, for example, this vector and then another vector, this is another vector. This is vector A and then this is vector B. So point of intersection is this. So the angle between these points of intersection. Assuming you have a vector of this kind, you have such a vector which is moving horizontally towards the positive x-axis. And then at its extreme end, where it started, there is another vector. This is the line of action of that vector. So what is the angle we are meaning here? We can go and push this direction for this vector, assuming this is vector B and this is vector A. So the angle between A and B is not going to be this. It is going to be this angle. Have you seen? Have you seen that? Very interesting. Now, assuming you have another kind of vector. You have this vector, okay? Yes, that is its line of action. And then you have another vector in that kind of arrangement. This is its line of action. So the angle between these two vectors is going to be towards the point of intersection. And this is going to be the angle between these two vectors, assuming one is A and another one is B. Very interesting. Now, when does the angle become obtuse? Because all these ones we are seeing, they are acute. The angle can be obtuse. How can it be obtuse? Assuming I have a vector of this kind, assuming it is moving in this direction horizontally, and there is one which is moving away from the tip of this, and this vector is moving in this direction. Assuming this is vector A, this is vector B. This is the line of action. That is the line of action which is always in the direction of that vector. Hope I've drawn this very well. Very well. So this is the direction and this is the direction. So the angle is now going to be this. This is the angle between vector A and vector P. And in this case, it is going to be obtuse. It is going to be obtuse. Very interesting. I'm still adding you more notes about this scalar product form of a vector. After getting the facts, then we shall go to the example. So let us clean this board and then try to add more of the notes or the facts about scalar product. You should also know that if somebody gives you A dot B, you need to write big letters for people to see. if it is A dot B, this is the same as B dot A. Okay, so the dot product is commutative. Now, if somebody gives you A dot A, this is the same as A squared. A squared, and this is the scalar magnitude of A. That's what it means. Very interesting. Now, assuming somebody gives you A dot, we have a scalar, okay, and then a B. A vector B is attached to a particular scalar. This is the same as, you can factorize out the scalar to get A dot B. Okay, and also it is the same as saying you can as well attach the scalar to A and dot with B. Here the scalar was attached to B, so you can attach the scalar to A and then dot it with B. So this is also a fact, a very, very interesting fact. Now, if somebody gives you A dot, for example, B plus C, a dot is like multiplication, so people should note that. So this A is going to dot with B, and also it dots with C, but don't forget the sign in between. So this is going to be A dot B, then plus A dot C. Okay, that is very, 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 very true. Now, assuming you have A, okay, plus maybe B, A plus B. Note this very well. And it is dotting with a C plus C plus D. How can we simplify this? It is like multiplication. A is going to dot with C, okay, and the same A is going to dot with D. But taking in account of the signs, B is going to dot with C, and the same B is going to dot with C. With D, such that we have A dot C plus A dot D, then plus B dot C plus B dot D. This is very, very correct. That is very correct. Immediately after a break, we need to start off with examples. People need to know how all what we have noted is being applied. Don't go away, stay tuned. From the break, let us go for our first example. That is example 1. Find A dot B. We pronounce this as A dot B for each of the following. So we have vector A and vector B, 8 units as magnitude, and then 6 units as magnitude of B, and the angle between them is 60. Yes, that is towards their direction, which is very okay. So we shall go and tell the examiner that using the general dot product A dot B, which is A magnitude, B magnitude, cosine of the angle between them. So for part A, the angle between these vectors is going to be 50. So we are going to say that our A dot B is going to be the magnitude of vector A, but it is given. If it was not given and it is in the form Aij, then we will go and employ the previously learned method of vector magnitude, how to find vector magnitude and then get a scalar. Vector magnitude will always give you a scalar. So A is 8. Don't again put the parallel double lines because these ones mean obtaining magnitude of a vector. But we have already got it, we can employ a bracket. So into B, which is 6, then cosine of 50 degrees. So when we multiply, we shall get 8 times 6, then times the cosine of 50. This gives us 30.9. 30.9. 30.9. So therefore that is A dot of B. Now A was direct, but B is not direct. You need to employ the notes which I gave you. Look at these directions. Oh, you need to first go and get the line of action of vector A and the line of action of vector B. The angle between A and B is not acute. The angle is obtuse, obtuse, because this vector goes and then this one moves away from its tip. So the angle between them is this. So this angle is going to be the whole 180 minus 60, which is 120. So we expect a negative value. Okay, we expect a negative value. We say that once the angle between the two vectors is obtuse, then expect the answer obtained to be less than 0. Yes, that's what we say, because the cosine is also going to be less than 0. Now let us go and see. A dot B for part B is going to be vector A magnitude, which is 4, into vector B magnitude, which is 5, then into the cosine of the angle between, which is 120. And that will only be seen by those who are serious with the mechanics. That is now a note, which is a fact. Once you fail to take this fact into consideration, your answer is not going to be correct. Okay, so we are going to see that the cosine of 120 is negative a half, or negative 0.5, or you can put it on the calculator. Cos 120, indeed it is negative 0.5 times the 20, which will give you a negative 10. So therefore A dot B is equivalent to negative 10. So have you seen? That's how we have started with our examples. Clear posture is provided for you. You can write. Control print. Yes, you can print the screen.